Good evening, ladies and gentlemen. It is my extraordinary pleasure to welcome you all here to the fabulous Laurie Auditorium. My name is Nirav Mehta. I am a professor here in the Department of Physics and Astronomy. For the past few weeks, my students and I have been preparing a host of physics demonstrations for you to observe this evening, ranging from electricity and magnetism to mechanics to fluids to waves. So we hope that this evening will be both educational and entertaining for you all, and we're ready to get started. So I want to begin with the basics. Let's get the slides back up, please. This is Isaac Newton. Isaac Newton postulated 3 laws of motion, and I want to just describe these briefly so that for the rest of the evening you have these in the back of your mind and you're thinking about them a little bit as you observe what you observe. So the first law is that you need a force in order to change the motion of an object, right? So here I've got a tennis ball, and I'm twirling this tennis ball around and around, and the tennis ball is following a circular path. It does not want to follow a circular path. It wants to go in a straight line. If we were in interstellar space, the tennis ball would be going in a straight line without any string. So as soon as I let go of the tennis ball, what's going to happen? It goes in a straight line. Sort of in a straight line, right? What happened? It followed a parabolic arc and hit the ground. Does that mean there's a force on it? Absolutely. There's the force of gravity. Okay, if we were in interstellar space, it would have gone in a straight line where there's no force on it, right? Okay, that's the first law of motion. You need a force to change the motion of an object. The second law, force is equal to mass times acceleration. Really, the left-hand side is the stuff that you do to the object. It's the pushing and the pulling, the forces that you apply, the pushes and the pulls. The right-hand side is all about the motion of the object. So mass, what is mass? Mass is how much stuff there is. The more stuff you have, the more mass you have. The acceleration is how its motion is changing, how its velocity is changing, okay? So here, Angela is going to help me demonstrate this. So Angela's going to come on here, and I'm going to give her a push. So I'm applying a force, and what do you think is going to happen? Her velocity is going to change. She's going to accelerate forward, and she's going to keep going until there's a force applied to her. And wait, is she slowing down? What's the force that's acting on her right now as she slows down? Friction, you guys are brilliant. Okay, friction is the force that did that. Yes. The third law is Newton's third law. The force of one object on another is always equal and opposite to the force of that object on the first object. Okay, so to demonstrate this, I'm going to attempt to stand on a skateboard. There we go. Okay, now, Angela's going to push on me, but I am not going to use my hands to push back at all. And we'll see who's going to accelerate. If anybody accelerates, they had a force on them, right? So if I don't push back, presumably I should stay here. Let's see what happens. And presumably Angela should stay where she is. Whoa! We both moved. We both began to move. So there was an acceleration on both of us. That means there was a force on both of us. I didn't use my hands, but as soon as she pushed on me, there was an equal and opposite force on her. Okay? So those are the 3 laws of motion. We will observe all kinds of phenomena this evening with these laws of motion. So I want you guys to keep those in mind. So now, John, I'm going to welcome John to the stage. Okay, so John's going to set up some styrofoam cups here. Let's go to the next slide, please. Okay, stuff is made of atoms. That's the first thing I want you guys to appreciate. If we zoom in on somebody's skin, you see skin cells, you see the cell nucleus, you see the DNA inside the cell nucleus. DNA is made of molecules. Molecules are made of atoms. Atoms have atomic nuclei, which are made of mostly empty, there's the atomic nucleus with protons and neutrons and some red, blue, green stuff in the middle. Okay, so atoms are made, stuff is made of atoms. This is the basic picture of an atom, right, John?
Yes.
Atoms have mass.
That's why you weigh so much.
You know, I go to the gym, I try to eat right. They also have charged particles in them.
Yes, they do have charged particles. Internal to the nucleus, there are protons, which contain positively charged subatomic particles. And around them, there's these electrons that orbit. Technically, they don't orbit, but we don't care about that. And they orbit, and they're negatively charged, which cancels out the charge of the proton, hopefully. Outside, you can combine or increase or decrease the number of protons to change the molecule it is on the periodic table. So this one has 2 protons, therefore it is helium. If you wanted to increase it further, you could create all sorts of different elements that the world is composed of. And finally, whenever you have 2 or more molecules, or 2 or more atoms, you combine them to create a molecule.
That's right. So now that we know the basic structure of matter, matter's made of atoms, and this is what atoms are made of, and we know that atoms have mass, we can demonstrate that atoms have mass because they're going to push on other things, right? I have a very special device here. This is an air cannon. What do you think it shoots? Air. Let's see. Let's see this thing in action. So I'm going to try. I think there's a sight on this.
Doesn't work very well.
Oh, look at that. Oh. So I'm going to try to knock down these styrofoam cups and... Oh, the first time.
First shot.
Boom.
Well done.
So, you might imagine that this thing shoots this sphere of air that kind of goes, it's like a ball of air, right? Like in Street Fighter or something. So, but no, the stuff that comes, sorry, John, sorry. The stuff that comes out of this, the structure of the air that shoots out of this thing is way more interesting than a sphere. It shoots, slide please. It shoots a vortex ring. So it's this ring that rolls through the air, and because it's rolling through the air, it is very good at conserving its kinetic energy, and it seems to last for much longer. It doesn't dissipate. It kind of rolls through the air. So it's really hard to see because air is invisible, but I have here a fog machine, so I'm going to try to fill this with fog. I have a little remote here. Okay, so let's see if we can knock this down again with the vortex ring.
Oh. Nice. Oh!
Ooh. You guys see that, right? Cool. All right. So I don't know if that was big enough. You know, we're in Texas, so let's go bigger. That one, you know, you can buy one of these on Amazon, but I decided to make my own. So let's see if we can do this. Could I get Amber out here to help? Welcome, Amber. I don't know if that's enough. All right. Okay, cool. So let's just see if you guys can see these rings here. Okay, cool. So in front of this thing, you guys can see the hole I cut out of this. Oh, sorry, Amber. You guys can see the hole. Like, what shape is the hole? It's a circle. Okay. What if we put a mask on here that is a square? What do you guys think will happen?
We'll get a square.
Let's do the experiment. I thought it'd be a triangle or something. I was like, still a circle. The circle must be a really stable shape, right? Let's try a different shape. What if we have, I think I'm running low on smoke. Let's refill here. Let's try a different shape. What's this shape, Amber? Okay. Let's try an oval. What do we think will happen? Did we get that? It's kind of jiggling. It's a jiggling circle. So this kind of jiggling, it should be jiggling up and down and back and forth. It should be kind of going wah, 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 wah. That's something we physicists call a quadrupole oscillation. The mathematics that govern quadrupole oscillations is exactly the same as the mathematics that govern the propagation of gravitational waves through space-time. So that's pretty cool. Okay, so now I'm going to turn this discussion of what happens with air and air pressure over to Ryoma, who's going to demonstrate air pressure for you guys.
All right, good evening, everyone. Thank you. Okay, so now he's explained what the air really is made of. It's made of all the molecules. I'd like to introduce this idea of pressure. I'm pretty sure everyone has heard of what the pressure is, but I want to use these balloons and the bed of nails. This is basically like a wooden board with a bunch of nails sticking out from it. I like to use these to demonstrate what the pressure really means. So if I were to press this balloon down on the bed of nails, what do you guys think would happen to the balloon? I guess options are pop or not pop, but let's try it. So first, I'm going to try to press this balloon on let's say one of the nails in the very corner, and let's see what happens. It pops. You guys were right. Next, I'd like to press it's the same type of balloon. Now I'm putting on the center of the bed of nails, and I'm gonna do the same thing. What do you guys think would happen to the balloon this time? Okay, let's try. Okay, I don't know if it's easy to see this, but I'm pressing on the balloon pretty hard. Definitely harder than when I popped the other balloon. Oh.
Try it again.
Let me try again. I think I pressed a little too hard on the last one, but despite pressing it pretty hard, it's not gonna pop. The reason for that is because when I put it in the middle of the bed of the nails, the pressure is low. And the way I want to define the pressure...
Slide, please.
The way I want to define the pressure is as force per area. And what do I mean by that? So here I prepared two diagrams of two rectangular blocks. Both of them have the same weight, exact same weight. But the difference is that the right one is touching the ground at a bigger area than it is on the left one. And on the left one, the weight is all concentrated in a smaller area. So the force per area, the pressure, is bigger on the left one. The idea is the same thing for this balloon. When I pressed it down on one of the corner ones, only one nail was touching the balloon, so all the power was going into one of the nails. But when I put it in the center, a lot of the nails are supporting the weight, so the pressure was much, much lower, and that's what prevented the balloon from popping. So what exactly is this force that I'm talking about in terms of the air molecules? So here's a cool simulation. So in this simulation, if you pump some air into the box, you're gonna see some blue balls bouncing around in the box. These blue particles represent the air molecules. Notice how they're moving around in random directions, bouncing off each other, bouncing off the walls. And how it hits the walls and applies force to the wall is what we call the pressure. And if we decide to put some fire on there and raise the temperature, the air molecules are going to start moving faster. If you notice, they're moving much faster, and they're hitting the walls much harder than when it was when the temperature was lower. And as you raise the temperature, the pressure is going up, because remember, pressure is force per area, and because the molecules are hitting the walls harder, the pressure is higher. Now let's try to cool down again. And as you expect, the molecules are moving slower than when it was at a higher temperature. Now, if you keep increasing the temperature, increasing the pressure at the same time, and let's keep doing that and see what happens. This little box has a lid at the very top. And eventually, if we keep increasing the pressure so the molecules are hitting the walls harder and harder, eventually the lid comes off because the air molecules that are on the outside are not able to combat the molecules hitting from the inside with the same amount of force. And the air molecules are going to go out because the pressure was too high inside. And now we're going to do a little bit of a different situation where we prepare like a little box inside this, a little box inside the bigger box. And let's see what happens if we try to extract all the air molecules from the little box. And John is going to explain that and going to show you a demonstration related to that as well.
Thank you, Ryoma. So what's happening is that we're going to be, in this situation, all the molecules inside this little square here, a rectangle, this is a rectangle, will be removed. And so if you press play whenever that occurs and run the simulation, all these molecules outside of it, outside that little empty rectangle, will start to bounce off and hit it. And that's going to apply a lot of force on that little square, or that little rectangle. Very good at shapes. And so, you might be thinking, that can't be a lot of, pressure, and that can't be a lot of, that's not a lot of force, probably. It's just, air hitting it. So I'm going to show you actually that is a lot of force if you take out the air inside of, for instance, this rectangle, or in this case, this metal drum here that's really durable, actually, as you probably heard. And we're going to use a vacuum to pump out all of the air inside of that. And what do you think is going to happen whenever that happens? Do you think it's going to, squish maybe a little bit, like a little water bottle that you have a little bit too little air in and it starts to squish around, or do you think it's going to crush? Crush it. That's what we like to hear. Enthusiasm.
Are you sure? I mean, this thing is pretty tough. I mean, we'll see.
We'll see. So, attaching the nozzle to the drum, hopefully. And switching it on. Baby, it's not plugged in. We're brilliant.
We need power, Captain.
Oh. We're not breaking anything back there, I hope. Oh, there we go.
All right.
Turned it off.
All right. Fire it up.
Oh, you heard that? Little pop. It's running. Oh. It's getting smaller.
So we're removing the air on the inside, and the atmospheric pressure is crushing this.
Crushing it. There's no molecules to oppose all this atmosphere out here, so it's just gonna shrink it down to a small little box. Bit frightening, honestly. I think that's about as small as it's gonna get, honestly. Don't know how I can. So.
I'll pass this around so you guys don't think I'm making this up.
Yeah. The power of air is very strong. So now I'm going to invite my friends Amber and Claiborne onto the stage along with my assistant.
Slides, please.
Ryoma. And we're going to do something actually a bit different with it. Oh, there's a ping pong ball rolling around. Thank you. And so, yeah, absolutely fine. So we're going to be using this leaf blower here. Claiborne, you want to turn it on? You can hear it. It's rather slight, but And we're going to be basically putting, not yet. We're going to be putting the leaf blower in between these two sheets of paper. And we're going to turn it on, and it's going to blow air. What do you think is going to happen to these pieces of paper? Are they just going to blow around in the wind? Are they going to push away from each other, going to pull towards each other? What do you think is going to happen? Push away? Push away, push away. I'm hearing a lot of that. Towards? Okay. Many different options.
Let's do the experiment.
Let's see it. So let's turn it on. Maybe. Turn it on high, maybe? Oh, there we go. They're being pulled towards each other. So there's, what's going on here? Why are they being pulled towards each other? So there's a principle in physics called Bernoulli's principle. Bernoulli's principle states that higher velocity fluids, air is a fluid, create areas of low pressure. And so what's happening is the atmosphere around it is wanting to go towards that area of low pressure, as we saw with the drum, wherever there was no air, so there was almost no pressure. And so the atmosphere wants to reach it, but it can't because these pieces of paper are in the way. So it pushes the pieces of paper towards this stream of air and causes them to stick together. So that's Bernoulli's principle in effect, if you want to see it again. We're not screwing with you. This is the thing. So hopefully that was interesting. And now we're going to be demonstrating a slightly different principle. Well, the same principle, but in a slightly different way. So I'm going to hand it over to my boy Ryoma, and he's going to hopefully, explain this very well.
Okay. So the Bernoulli effect, like John explained, is basically saying that the air that's moving at a faster speed than the surrounding air is at a lower pressure. And this effect we can apply to another thing, another cool demonstration which John is going to show. So he has a little ping pong ball and a straw, and he's going to blow some air through the straw and try to float the ball above the straw. Yeah. So why does this happen? If you look closely, the balls are wobbling, right and left, just a little bit above the straw, and you might think it should fall off from the side. The reason why this doesn't happen is because of Bernoulli's effect.
Slide, please.
Okay, so when John blows some air through the straw, the air comes out of the straw and hits the ball from the bottom, and it spreads and creates a flow of air where it's moving faster than the surrounding air. And that low pressure region created by the flow of air surrounds the ball. And whenever the ball wants to fall off from the side, the air that's at a higher pressure around that's outside of the flow of the air is going to want to come back towards the low pressure region, and that force pushes the ball back into the stream of air. And that's what allows these balls to float above the straw. But with the camera, you might be able to see, but I know it was a little bit small, and I know Dr. Mehta told you guys earlier that we're in Texas, we got to do something bigger. We prepared a leaf blower and a beach ball to do the same demonstration. So let's give it a try. Okay. Notice how the ball is floating above the leaf blower, even though it's at an angle. You might think it should fall off, but it doesn't. The logic is the same thing. As I explained earlier, the flow of air that's surrounding the ball is going to protect the ball from falling to the side because the air surrounding the ball wants to come toward the ball where the air is moving faster. And I have a little eraser right here. Okay, John's moving. 1 second. Okay, so I have a little eraser here, and I like to throw this eraser at the ball and see what happens when we apply some force from the side to the Bernoulli's, to the ball that's floating around. Let's try. Yeah, one more time. Okay, we're good. Okay, even though the eraser does apply some force to the ball, the pressure trying to come towards the low pressure area is strong enough to keep the ball floating around, and that's the cool thing about Bernoulli's principle. Yeah, that's it from us. Thank you so much for your attention.
Woo! All right, thank you, Ryoma and John. Now, I talked earlier about how most of the stuff that's making up the air in this room is nitrogen gas. It's about 78% nitrogen, 21% oxygen, and about 1% other stuff, something like that. So when you get nitrogen really, really cold, how cold? Let's see. I think I have a slide. Ah, yes. These, I've got 3 temperature scales here. Fahrenheit for everybody who lives in the US, Celsius for Europeans, and Kelvin for scientists. So on this scale, water boils, when water boils at 212 degrees Fahrenheit, 100 degrees Celsius, 373 Kelvin. Body temperature is about 100 Fahrenheit. Water freezes at 32. The big freeze last year got down to what, single digits in Fahrenheit, right? That was pretty cold. You got to go another 100 degrees colder than that before you get to dry ice. You can buy that stuff at the grocery store. It's really cold. Don't touch it too long because you're gonna get a burn on your finger and it'll stick to your fingers. And then you got to go really cold to get down to liquid oxygen, liquid nitrogen temperatures, right? So at minus 321 degrees Fahrenheit, nitrogen passes from a gas to a liquid. So I've got some liquid nitrogen right here, and I'm gonna pour some of it in this cooler. Now I'm gonna use these gloves because I don't want to burn my skin in case some of it gets on me. And then I'm going to stuff a couple of balloons in here. What do you think is going to happen to the balloons? You think they'll pop? What is inside the balloons? What's air mostly made of? What happens when it gets really, really cold? So let's see if I stuff this balloon in here, what's going to happen. In fact, I'm gonna do a little experiment. I want to see how many balloons I can get in there. So I'm going to put 3 in right now, and then I'm gonna go off backstage and keep working on the balloons. And in the meantime, Maddie and Sebastian are going to tell you guys a little bit about electrostatics. So let's welcome them to the stage.
All right, thank you. Hi, everyone. So right now, Sebastian and I are going to start talking about electrostatics. But first, remember what John and Dr. Mehta was saying earlier about how atoms have these charged particles inside of them. So all these objects are made of atoms, and thus you can have positive and negatively charged objects, but you can also have neutral objects as well, and you'll see that shortly. So the first demo we're going to do, you ever heard the phrase opposites attract, right? I feel like that's a pretty familiar one. So you can also have, or there's also the phrase that like objects will repel each other. So the first case we're going to do is a little bit of repulsion. So we have this fun fly stick. You can actually find it on Amazon. It's very fun to play with. I do recommend. So we have this stick, and so the stick is going to build up a charge at the end, and the Mylar sheet is going to build up that same charge. And so, since the Mylar sheet and the fun stick have the same charge, it should repel, and it's going to float. And so, it's light enough that it just kind of takes off a little bit. It does not want to be near the stick because they have the same charge. And so, it just kind of takes off and goes all over the place. But it's very fun to play with. Amazon. A little bit of a plug for the fun fly stick. And so we also have the case where you can have 2 objects are going to be attracted to each other. And so, a little short. We have here, so I have some rabbit's fur and I also have a PVC pipe. And so one way that charges can transfer from one object to another, changing the overall like positive or negative status of an object. So right now I have 2 neutral objects, the fur and the PVC pipe, but through physical touch, I can transfer some of the charge from one object to the other one. So I'm gonna charge this up really quickly. You have to do a little bit of rubbing to get them to, so what's happening actually is that the negative charges are jumping from the fur to the PVC pipe, leaving the PVC pipe overly negative, and the fur is gonna be overly positive with a deficit of electrons. back. So what's happening here is the can is overly neutral right now, but because it's neutral doesn't mean it has no charge. It actually has an equal amount of positive and negative charge. Sorry, my charge has dissipated as of now. But so the can has the same amount of positive and negative charge, and so by bringing the negatively charged PVC pipe near the can, it's actually drawing the positive charge, or the PVC pipe is negative, and the can is neutral. So it's drawing the positive charge from the can towards the negatively charged PVC pipe, and it's being attracted. So there we have a little case of repulsion and attraction. And so now we have another, we're going to introduce this thing called the Van de Graaff. And so this is one of our many metal spheres that we got here. And so we're going to use the Van de Graaff to charge up a larger metal sphere, and we're going to see if we can make this effective attraction a little bit bigger. Instead of a little coffee or little Coke can, we're going to use a coffee can. So we're going to give it a little bit of time to accumulate charge so we can see it in effect. And Sebastian has to be careful to hold it lower, his hand lower on the stick so he doesn't get zapped by the Van de Graaff here. Electricity is dangerous, guys. All right, so we're going to give it a go. And you can see it taking off a little bit. Yeah, so the can is actually a little bit heavier than the Coke can, so this is a pretty noticeable effect. You can see it. We're not touching it. It's not magic. It's just electricity. All right. And so now we're going to do another little thing with the Van de Graaff. But in order to do so, let's think about this, guys. So we just had two objects, and they were being attracted or repulsed from each other, but they weren't touching each other, but they were feeling that force. So how are these charges interacting even though they're not actually touching each other? There's this thing, actually, it kind of acts as the middleman. It's called the electric field. And so any charged object actually has, it creates an electric field in the space around it. And so you can think of an electric field as kind of like arrows pointing out in space everywhere from this object. So in the case of the Van de Graaff, actually, it's accumulating this positive charge on the surface of the Van de Graaff, and it's all the arrows pointing outwards are the electric field. So the closer you are to the Van de Graaff, the stronger the field is at that point, but the farther away from the Van de Graaff, the weaker it is. And so one way we can demonstrate the field in action is with this neon tube. And so this neon tube has some free charges on the inside, and they get excited when it's radially aligned with the Van de Graaff. So if we could dim the lights a little bit, you should be able to see the neon tube lighting up. But if the neon tube isn't oriented directly with the Van de Graaff, if we give it a little spin, you'll see it'll alternate between light and dark. Alrighty, so now I'm going to hand it over to Sebastian. We're going to do a few more trips with the Van de Graaff, and there may or may not be volunteer participation, so be on the lookout.
Thank you, Maddie. Now we have a few more demonstrations of how the Van de Graaff can interact with objects around it. Here we have a regular helium balloon. I'm going to put it close to the Van de Graaff, and then I'm going to turn it on, and we'll see what happens. Oh, the balloon gets attracted to the Van de Graaff, but as soon as it touches it, it gets pushed away. You see, the balloon gets attracted to the Van de Graaff for the same reason that the Coke can got attracted. It's neutral, but the positive charge of the Van de Graaff attracts the negative charge of the balloon. And then the moment they touch, there's a spark, because the balloon suddenly gets all the positive charge from the Van de Graaff. And now that they're both positive, they repel each other. So after a while, the balloon will lose all its charge, and then it'll be neutral again. So it'll start getting attracted to the Van de Graaff. And that cycle will repeat as many times as I let it. And now after I turn off the Van de Graaff, it's important to discharge it to get rid of any leftover charge. Otherwise, if I touch it, I'm going to get shocked. So I've got to be very careful when dealing with electricity, especially something as powerful as the Van de Graaff. That could really hurt. So now, I'm going to stack a bunch of these tin foil little pie tins on top of the Van de Graaff. And when I turn it on, all of the pythons, because they're touching the Van de Graaff, they're all going to get charged along with the Van de Graaff, and they're all going to be positive. So they're going to fly away one by one because they all repel each other. They're all positive, and they all fly away. As they accumulate charge, they start to repel each other, and the top ones start to fly away first. The bottom ones can't fly away quite yet because all of the top ones are keeping them down. So now we will need some brave volunteers that are willing to risk a minor shock. Yeah, with long, straight hair and above the age of 18 or with parental consent. Yeah, we can take 4 volunteers. So how about you in the front row? Right there. Yep, you, come over here. You can come over here. And let's see, who else? Yeah. And, well, we have 4 volunteers right here. Perfect. Now let's move these pythons out of the way. I'm going to clean them up later. So, you're going to need to stand on these milk crates. And don't get off the milk crates until I tell you to, because if you get off early, you might get shocked.
There is a non-zero chance of shock here.
Yeah, but if you follow instructions, you should be fine. You're not going to get hurt, trust me. So, volunteer number 1 here, right in front of the Van de Graaff, put your hand on the machine. And now you must all hold hands. Please get on the milk crate and hold hands with the other volunteers. So now you're all connected to the Van de Graaff. And when I turn it on, you are going to accumulate charge just like the pythons. But you're not going to fly away, obviously. So what's going to happen is your hair is going to start to stand on end because all the hairs are going to start to repel each other. And they're going to start to try to get away from each other. So here you can see the hairs are standing on end. They're all accumulating positive charge, and they're repelling each other. See? And you can feel the charge, can't you? Yeah, you can feel it. But that charge isn't going anywhere, so you're not getting shocked. It's only until the charge goes somewhere that you get hurt. That's pretty cool. Even though you're touching the machine, you're perfectly fine. So now I'm going to turn it off, but remember, don't get off the milk crates until I tell you to. So now the charge, you can let go of the Van de Graaff and each other, but don't get off the milk crates. We need to wait a little while for the charge to dissipate into the air before you can get off. Otherwise, you might get shocked. So just wait a few more seconds. 4, 3, 2, 1, and you're good. You can get off and return to your seats. Thank you very much. And great job. Now I got to clean all these pythons.
Let's check on our balloons. Let's see how they're doing here. How many do you think I got in here? I started with 3, didn't I? Here's 1. Here's 2, 3, 4, 5, 6, 7. What's happening to the balloons as they come out? 8, 9, 10, 11, 12, a little liquid nitrogen there, 13, 14, 15, 16, 17, it's like a clown car, 18, I think that's it. Okay, 18 balloons, not bad, not bad. So balloons, these balloons are elastic, right? They're made of rubber. So what happens as the nitrogen, the air inside there turns from a liquid back into a gas? It's going to exert more pressure as it turns back into a gas. And that means it's going to push out on the walls of the balloon, and the balloons are going to expand again, right? Until they reach a size where the inside pressure is equal to the outside pressure, right? So when that happens, they've reached an equilibrium. Now, the balloons are elastic, so they can expand. What do you think would happen if I put some liquid nitrogen into a chamber that is not allowed to expand, and then I cork it up? I'm going to blow the lid off like I did in the simulation. I'm going to blow the lid off. Well, we're not afraid. Let's do it. I've got here a little pipe. It's sealed off on this end. I'm going to pour some liquid nitrogen in here, and then we're going to cork it up, and we're going to see what happens to that cork. Okay, so Claiborne is here. He's going to smash that cork on with the hammer, and I've got gloves on, but he's still going to try not to smash my finger. And Rioma is going to play catcher. Okay. Oh, we need the liquid nitrogen. Okay, let me grab some liquid nitrogen out of here. Okay. Oh, that might not be enough. Let's get a second cup. It's so foggy, it's hard to see. All right, so I'm going to pour this in here. Set this down. Here we go. First cork. Second cork. It's a grounder. Boom! Okay, last one. All right! Wait, I got one more. Woo! All right, thank you, Rioma and Claiborne. So, boy, I'm starting to lose track. What's next? Can we advance the slide? That'll remind me. Do you have the slide advancer, Rioma? Thank you, sir. Okay, so now I want to return back to this image that we had at the very beginning. This is an image taken by the Hubble Space Telescope. It's one of the most amazing pictures ever taken. The Hubble Space Telescope trained its lens on a very minuscule portion of the sky. Balloons are a hit. I like it. Okay, so nearly every object you see in this picture is another galaxy. And I just point that out because it's just astounding. Every galaxy has probably 100 billion stars, some number of planets around each star. This is just an astounding picture. And I just want to point out that there are several galaxies that look a little bit like our own. They're spiral galaxies. And spiral galaxies, what do? They rotate about a core, about a supermassive black hole at the center of the galaxy usually, and a dense core of stars. And so this is a ubiquitous phenomena. As gravity pulls matter in, these objects begin to rotate faster and faster. And that has to do with a phenomenon called conservation of angular momentum. So you can see this happen in deep field images like this. And now I'm going to call to the stage Liz and Nathan, who are going to demonstrate some physics associated with angular momentum, conservation of angular momentum, and situations where angular momentum is not conserved.
Hello, everyone. All right, so how many of you have been in the car before when who's ever driving turns just a little bit too fast and you feel yourself kind of being pressed against the side of the car? I know my mom likes turning around corners really fast in her minivan. So the reason that you kind of feel like you're being pushed to the side is because your body doesn't know that the car is turned. So you're going to try to still be going in a straight line, but the car is turning in a circular path. So it's engaging in circular motion. And so here we're going to demonstrate circular motion using a bucket that's full of ping pong balls. And the ping pong balls aren't secured in there. If Nathan were to turn it, they would just fall out like that. But watch what happens when Nathan turns the bucket in a circle. And the balls will continue to go straight, but the bucket will be there. None of the balls fall out. Now, inertia is an object's resistance to change in its motion. The more inertia an object has, the harder it is to get it to start moving or to stop moving. And an object's angular momentum depends on its rotational inertia and on its angular velocity. So, since the rotational inertia depends on an object's properties of an object like its mass and its radius, Nathan's going to demonstrate what happens when changing the radius while he's spinning. So I'm going to go ahead and spin him around. And just like an ice skater, when his arms are out, he's going to be spinning around in a slower circle. Then, if he brings his arms in, he's decreasing his radius, and his angular speed is going to increase. This is because angular momentum is conserved, so it's going to stay the same. If Nathan brings his arms back out again, he's decreasing his radius. Is increasing his radius, and so therefore his angular speed is going to decrease so that its overall angular momentum stays the same. Perfect. A little dizzy. Now, hopefully Nathan's not too dizzy to demonstrate this next part. So this is the hover and spear, and you might have seen something similar in like a toy before, but we're going to use it to demonstrate what happens when you have a spinning object that you decrease or increase the radius of. So at first, we're going to have the spear not spinning, and when Nathan pulls the string, it's going to decrease the radius of the spear. Cool, right? Nothing really interesting, but we know how it works now. But here, watch when Nathan spins the spear. So when it's spinning, it has a large radius and a certain angular velocity. Nathan will make it smaller, and look how much faster it spins. So that's because, once again, we're decreasing the radius, so the angular speed has to increase.
Okay, for this next part, I'm gonna need a third person. So Liz talked about the impulse part, or the inertia part of the angular momentum equation. I'm gonna talk about the other part, the angular velocity. And angular velocity is a little bit different than speed. Can anybody tell me what the difference between velocity and speed is? Just like shout it out. Yes. So velocity is speed with the direction. So if I'm walking this way, this is like at like 2 meters per second, and then I turn backwards, my speed stayed the same, but my velocity changed. And the same thing can be applied to angular velocity as well. So Liz is gonna give this bicycle wheel an angular momentum. And you see, when Maddie just holds it straight up and down, there's no movement. And if you can think about this system from seeing it from above, you don't really see anything moving. However, if she turns it to one side, now, if you imagine looking at it from above again, the wheel is rotating in one direction. So to conserve angular momentum, the turntable has to turn in the opposite direction. This is because this is an isolated system, so there are no external forces acting on it. However, we can show you something a lot cooler if we, oh yeah. Thank you. So now we're going to look at a case where angular momentum isn't conserved. And this one blew my mind when I first saw it. So if Liz is holding this bicycle wheel, the center of mass of the wheel is some distance away from the pivot point, which is right here where the string is connected to the axle. And if she lets it go, it just falls and rotates about that pivot point. However, if we give this wheel an angular momentum, so if she holds it up and lets go, it precesses around that point. So the direction of this motion can be represented using what we like to use in math and science called the right-hand rule. So if I take my hand and I point my fingers in the direction from the pivot point to the center of mass of the wheel and curl them in the direction that gravity is acting on the wheel, my thumb is now pointing in the direction that the wheel will precess around. And depending on the direction the wheel is rotating will depend on which way, on if my fingers are pointing in the positive direction or the negative direction. And therefore it will depend on whether the wheel precesses in this direction or this direction, clockwise or counterclockwise. Thank you.
Yay! Okay, so let's get some of this stuff off. Slides, please. So now, I have a little game prepared for you that I like to call, Which Way Will It Roll? Okay, so I have a giant spool here. This spool has a rope wrapped around its inner radius. And currently, the rope is going around this way. I'll let you guys take a look at it. It's going around this way. And it comes out on the top side of this inner radius of the spool. If we can move there we go, if we can move that, yep, then I can show you. Okay, so I've got a pull here, right? So that's the way the rope is, and that's how I'm going to pull. Okay. Now this is actually a question. This is a quiz. So I want you guys to talk to your neighbor and confer with your family, your friends, and try to decide which way this thing is going to move. Okay. Okay, I hope you all came to a consensus. If you believe that the spool will roll to the left, say left. If you believe the spool will roll to the right, say right. Controversy. That's what we call in science a controversy. Okay, let's do the experiment. It went left. The lefts have it. Okay, cool. This time, slide please. Let's try it. Oh, I will point out that, let's go back to Newton's laws, right? I'm gonna have to say something about the forces involved. There are two horizontal forces that are acting on the spool, and in this situation, both of those forces are to the left. So it's no surprise. The spool went to the left. There's the force of my pull on the rope, and then there's the force of friction that the ground exerts on the spool, okay? That also points to the left. You can kind of imagine the spool wanting, if I pull, right, the spool's going to kind of want to rotate like this. So when it rubs up against the ground, it's going to want to push the ground that way. But the ground is going to exert an equal and opposite force by Newton's third law on the spool in the opposite direction this way. Okay? So both of those forces on the spool are to the left. Okay, next slide. Which way will it roll? Talk to your family, your neighbor, your friends. This time I'm going to pull up, straight up. Okay, if you think it's going to go left, say left. If you think it's going to go right, say right. Oh, I think the lefts have it. Okay, let's do the experiment. Oh, it went left. In this case, there's only one horizontal force. Which force was it? Friction. Which way was it pointing? Same direction as before. That way, right? Okay. Now, let's try it one more time. Now, the rope is coming out the bottom, and I'm going to pull this way. Okay? Which way will it roll? Okay, if you think it's going to go left, say left. If you think it's going to go right, say right. Ooh, controversy once again. Okay. It goes to the right. It rolls up the rope. It's doing my job for me. So I love this demonstration because I was surprised when I first saw this demonstration. And sometimes the simplest things in physics will surprise you. And if that kind of thing brings you joy like it does me, you should become a physicist. So, I want to say a few words as I roll this off the stage about Michael Faraday. Michael Faraday made some of the most important contributions to electricity and magnetism. He made one important insight, which actually powers all of your home devices. He said that a changing magnetic field will create an electric field. And that electric field can be used to push around current. And that current is what you use to power all of your devices, your phones, your toasters, everything. And in fact, this principle can be used to make an electric motor, right? And if you run the motor backwards, you have a generator. So this is how we create electric power all over the world. And this is how we use electric energy all over the world. And to demonstrate this idea, I'm going to let Amber and Angela take it away.
All right, so to start, we kind of have a question for y'all, and that is, how many of y'all have a wireless charger, a wireless phone charger, or at least know what one is? Okay, that's a pretty good majority. So the funny thing is that these Faraday's laws and these concepts about electricity and magnetism and how they're intertwined, that's really important to how things like wireless phone chargers work, because the moving electric current can actually create a magnetic field, which we refer to as an electromagnet. And when you have an electromagnet next to a conductor or another electric wire of some type, it can induce another electromagnet in that, which is how you have this sort of wireless charging system. We've got a couple of different ways we're going to demonstrate this type of concept.
So what we have here is a device that does exactly that. This is coils of copper wire that's receiving an alternating current from the outlet, just like any outlet. And what that alternating current does is produce a changing magnetic field, which in turn turns this into essentially an electromagnet. Now, if we were to put a ring of aluminum being a conductor, but not magnetic, when it interacts with that field, if we can get the slide for a second, it also produces an electromagnet, but facing the opposite direction. So it's kind of like having two north poles of a magnet against each other. And what they'll do is they'll repel. Shall we see it? That's pretty cool, right? And the effect is not specific to aluminum. Here we have a copper ring, which is just like the aluminum. It is also a conductor and not magnetic. This one's a bit heavier, so it doesn't go quite as high. And like your phone chargers, here we have coils of copper wire. And when you put the copper wire into the electromagnet, can I hand you the mic for a second?
Of course. Is there any way to dim the lights also so we can see this really bright? Thank you.
So what happens here is the magnetic field induces electric current called an eddy current in this copper wire, just like in the aluminum ring. And that in turn lights the bulb. And because it's an electric current, it goes around in a circle, just like normal electricity. So if you have... So if we can have lights again for a second. Here we have another aluminum ring, but this one's a little bit different. If you can see, you can't really see, but you'll have to trust me on this. It has a slit through the side, so it doesn't make a full circle, which means that the eddy currents can't make a full current. So what do you think is going to happen? It's going to spin, you think? Let's see. Nothing. Nothing happens because it can't make a full circuit. You know what I want to see?
What do you want to see, Amber?
I want to see it go higher.
I do too.
How do you think we can make it go higher? That's a good answer, but you know what else you can do? Here's a cue here. Yeah, you can make it colder. Because making it colder will make it a better conductor, which will make it a more powerful electromagnet. So what we'll do here is we're going to dump it in the liquid nitrogen. It shouldn't take very long.
Yeah.
Yeah.
It gets cold really fast.
All right, and I'm going to not catch this one because I do not have protective gloves and it is very cold. You ready?
One more time?
One more time? All right. Now, let's look at the same effect, but in reverse. So what we have here is an aluminum tube, just like those little aluminum rings, but much bigger. And here we have a small and surprisingly powerful electromagnet, or normal magnet, that may interfere with the camera. We will see. And what happens when we drop it through the tube is, as it falls, it produces a changing magnetic field, which creates those same eddy currents in the aluminum tube. And that energy comes from the kinetic energy of the falling magnet, which will make it, what do you think will happen? Slow down? Yeah, let's see. Levitate and spin? Let's see. Kind of cool, right?
Goes pretty slow.
Should we make it bigger?
Always.
Always? Yeah.
So Amber and I have created this device here. We've created a few different names for it. We call it the swinginator, the swingatine. There's a few different things you can refer to it as. And what we have is we have two different beams holding up different sheets of aluminum. This back sheet here has slits in it, kind of like that ring over there that had a slit through the middle. This one has a lot of slits in it. And this one is solid. So we're going to kind of observe how these things swing. Obviously, with no magnets interacting with them, they swing really well in tandem. And now we're going to add some very strong magnets that are going to be kind of in between. They're very strong. Hopefully we can assemble them without getting hurt. They're going to be placed so that the aluminum sheets are going to pass through them. And we're going to see what happens. So let's go ahead and take a look at the slitted aluminum sheet first. Now, we saw that nothing really happened earlier with the slitted coil, or sorry, the slitted ring of aluminum. So what do you guys think is going to happen here? Just going to swing? All right, let's see. You guys were right. It's pretty unaffected. Now, let's see what happens when we swing them both at the same time and see what happens to the solid sheet of aluminum. What do you guys think is going to happen? Let's have a vote of two. The first vote is that it's going to swing faster. Maybe it'll do a loop-de-loop even. Well, I guess it would hit the bar, but who thinks it's going to swing faster? Got a few hands. Who thinks it's going to slow down? More hands. All right, let's see what happens. Go. You guys are right, it slowed down. That's Newton's law, by the way, not electromagnetism. All right, let's try again. Third time's the charm, right? We had a little difficulty building this and getting it stabilized, so we're doing our best.
All the engineers, I'm sure, will appreciate that.
Yeah, we're physicists, not engineers. Well, you guys can kind of see it slowing down a bit, I think. We'll try a few more times to see if we can get it. But the effect you might still be able to notice. Very strong magnet again. There we go. Slows down completely to a stop. Good job, Amber. This is a phenomenon that we actually call eddy braking. Now, how many of y'all have ever ridden a roller coaster before? All right, that's a lot of people. They're pretty popular. So, eddy braking is actually the main mechanism, or one of the main mechanisms that they use to stop roller coasters. So you're essentially riding this conductor.
Sorry.
You're riding this big conductor, and there's a bunch of magnets at the end of the ride that help you come to a stop without applying any mechanical forces that wear down over time. So we have a slide here. You might be able to see the magnets.
Oh. This one? This the one you want?
Maybe. No, more.
This one.
One more.
This one.
There they are. You guessed it. That's where they are. That's where the magnets are. And that's what Amber and I have to show you about electromagnetism.
Thank you, Angela and Amber. Okay, so I'd like to call Claiborne onto the stage.
Explain to you a phenomena that you guys are currently experiencing, all right? This evening, you guys experience this all the time, but you may not think about it, all right? And so this evening, my hopes are to explain this to you in a way that you may not have thought about, okay? And so my first question is, how many of you have been to a water park? Have you guys ever went to the giant pool at the water park? Yeah, you've been to the giant pool at the water park? Well, okay. What happens when you're at that giant pool and the buzzer goes off? Who can answer that? Oh, yeah, exactly. What'd you say? What was that? A wave. That's right, a wave. And that's exactly the phenomena I want to explain to you tonight. Okay, so, initially, we had another guest who was going to assist us with this demonstration, but unfortunately, she wasn't able to help us. So, instead, I have your amazing host, Dr. Mehta. All right. And so what we have here is a slinky. And this slinky is basically a guitar string, okay? So this is the same phenomena that a guitar, violins, any type of string instrument experiences. Banjo, there you go. What's the other one? Dan bow, there you go. Okay, so here we go. So what I'm going to do is create a traveling wave, okay? I'm gonna send a pulse down to Dr. Mehta. And let's see what happens when I do that, all right? So when I send the pulse down to Dr. Mehta, it actually travels back to me. And the speed at which this pulse travels is dependent on the tension in this string, okay?
So if we make it slack,
it'll move a lot slower. Well, let's try and send another pulse. And then let's come back out here. Okay. So now it's moving a lot faster. Okay, so let's see what happens if I send a pulse when it actually makes it back to me. When I send the pulse, at the same time the pulse reaches back to me, you see it gets a lot higher. And this is what we call constructive interference. And what's actually occurring is that the two pulses are adding together. And we physicists, we like to use complicated language, so we call this a superposition of the two waves, okay? And so that's constructive interference. Let's try and slow this down. Okay. After we do that, let's see. And if I can oscillate my hand at the correct frequency, we'll get, instead of traveling waves, we'll get this thing called a standing wave. So let's see if we can get that for you. So if I can oscillate here, and you want to do it up higher. This is the first fundamental node of this wave, of this string, of our wave here. And so if I move it a little faster, we can get 3 nodes in there. And if I move a little faster, let's see if I can get it. There we go. Oh, there we go. And you see the wave's not traveling. It's just standing in place. And so that's a wave, you guys. So that's what I wanted to show you. And so, if we can get my, yes, slide.
Speakers. Oh, slide.
Yes. And so now Dr. Mehta wants to actually show you this demonstration, and I'll try and explain it to you. So let's see what happens here. So as you can see here, we don't have this. Instead, we're going to have water droplets. So you can actually do this experiment at home for yourself. You can just fill up your tub with some water, plug it, of course, and then afterwards, let the faucet drip a little bit. And what you'll see are spherical waves, just like this. Okay? You'll see these spherical waves. But what happens if you have 2 of them? When you have 2 of them, the droplets from this one will create spherical waves that propagate out in the water. And the droplets from the top one will have waves that propagate out into the water. But when they meet in the same place, the 2 waves will interact in the same fashion that we just showed you. They will either constructively interfere or they may destructively interfere. And it really depends on the path that it takes for the 2 to travel. Yes. And so, what we have here set up is actually an experiment that duplicates this. But this time, we're going to use sound. And sound is the phenomena that I would like to explain to you this evening that I kept as a mystery. See, this sound I claim that it's a wave. And if sound is a wave, then it should behave in the same fashion that those waves behave. And don't plug it up. So let's see if this actually, so let me explain sound a little further. So what actually happens when you have sound waves is the molecules in the air, we spoke about this, but they're actually propagating throughout this room, and they're bumping into each other, and they're propagating throughout the room, and your ears, the hairs in your ears receive that signal, and your brain interprets it as sound, okay? And so what we have here are two speakers, two loudspeakers, and they're spaced at 1.5 meters apart, and here we have a function generator. This function generator has been set to 3,000 hertz, okay? And this is a frequency, it's pretty high, but you can bear with it. And what I claim is that the sound will interact with each other, it will interfere. So you'll get places where there's constructive interference, the sound will be louder, and then you'll get places where there's destructive interference. You may not hear anything, it will be fainter, okay? And you can actually calculate this, but I'll let you do that when you make it here to Trinity, and in fact, I'll show you how to use one of these function generators. So let's see if this happens. Let's see what happens. So now we have sound from one speaker. And sound from the second. Okay, and what I'll need you to do in the audience, I want you to just rock back and forth ever so slowly. However, I need you to cover one of your ears, okay? That way you can find where the nodes are, where those peaks and where those valleys are. But when you find one of the valleys, just stay there. I want you to just hold that position. And the further back you are, the further out you would actually have to go. If you're actually sitting up at the front row here, you only have to travel like 19 centimeters. But if you're further back, you have to actually go pretty far. You might have to go like 2-3 seats over. So, but when you get that node, just let me know. Okay, well, it seems like a couple of you have it. I'm not sure if everyone in here experienced it, but I certainly did. So, you know, that's my story. You heard everything I had to say this evening. So, I'll let you guys go. But I want to say thank you for your attention and that you've been a great audience.
Let's give it up for Claiborne. Slides, please. Oh, I gotta quit out of this simulation here. Where's my mouse?
We all clean this up, right? You got this? Well, I don't know how I'm gonna get that.
There it is. Phew. Okay, you guys remember this game? Which way will it roll? Okay, so let's imagine I'm standing on a cart, okay? And I'm chucking racquetballs or something with a little heft, right? And I'm chucking these balls towards this wall. The wall is also mounted on the cart. And the balls bounce off the wall and go over my shoulder behind me, okay? Which way will the cart roll? If you believe that the cart will roll to the left, well, actually, think about it. I'll give you the thinking music. If you believe the cart will stay still, that's a valid option too. Okay, if you believe the cart will go left, say left. If you believe the cart will go right, say right. Okay, all right. Well, I have an experiment for you, but I'm not going to throw balls. I'm going to throw carbon dioxide molecules. Because I have here constructed a cart. I will sit in this cart. I will wear a bicycle helmet for safety. And this carbon dioxide, this is a carbon dioxide fire extinguisher. It's a little bit different from the extinguishers you have in your home, which shoot a chemical that's designed to put out the fire. This fires pure carbon dioxide. And the idea is that it will displace the oxygen and put out the fire, okay? So basically what's coming out of this is pure carbon dioxide, and it gets really cold when it comes out, so it's gonna look a little bit like dry ice, like gaseous ice, like dry ice. So I'm gonna remove the pin. Okay. All right. And I'm gonna sit down. This doesn't have any brakes, so actually I'm gonna reposition this because it's gonna curve a little. Oh, nobody sitting here, that's good. You guys should be safe. You may get a little bit of CO2. Here, all right. There we go, okay, here we go. Which way will it go? It's gonna go that way. It's gonna go that. If I shoot it this way, which way will it go? Oh, I better turn it around. Okay. All right. All right, here we go. I'm gonna hold this down. Nobody behind me, right? Nobody went to the bathroom about to come back? Okay. Woo! Can I stop? My foot got really cold with that one. All right. All right. So I have one more demonstration for you guys. I want to revisit Rioma's bed of nails. Can I have the slides, please? So let's revisit the bed of nails. I want to really impress upon you that when you distribute the weight over enough nails, it's perfectly safe. Okay? So I'm going to lie down on the bed of nails. And I'd like a volunteer. How about you, sir? You, sir, please. I hope you all have enjoyed the show. I have one slide that I'd like to show. So this show would not have been possible without the help of so many people. Ryan Hodge from the from the Makerspace helped us make a lot of the stuff that you saw today, and helped us set things up, and he was real phenomenal. Lexi Baum and Matt Heimer from the Chem Stock Room helped us get chemicals and liquid nitrogen. Kevin Hawkins, the director of Laurie Auditorium, let us use this wonderful facility. Mary Helen Casareno Perez did all of our purchasing for us and was just phenomenal. Adam Urbach lent us his vacuum pump. Les Bleemaster got me the chair I screwed into the cart. David Pooley fixed our Van de Graaff machine. Jennifer Steele and Oren Schindel, just overall supportive. Josh Maxagemba did is helping us with the camera work for tonight. Richard Silver helped us move all the stuff from Mars McLean to Laurie. And the Laurie Auditorium crew has just been phenomenal tonight. And then finally, yeah?
And we would like to thank you for being a wonderful teacher, a wonderful professor, and putting all of this work towards this process.
It's been my pleasure.
It could have been done without you.
So, thank you guys. This is delightful. Oh my gosh. Thank you. So I want to call everybody onto the stage. Liz, Sebastian, Rioma, Madison, John, Claiborne, Angela, Amber, Nathan, and myself. Let's give everybody a hand, please. Let's take a bow. Thank you guys for coming tonight. Hopefully this will not be the last amazing physics show, so keep your eyes peeled for more in the future with more fun and more physics. Thank you, good evening.